yesterday we basically took a broad view on the gravity, and we compared Newton's and Einstein's theories of gravity. And we basically wrote a summary table where we wrote down the fundamental quantities, the equation of motion, that we described the tidal tensor and the field equations for these two equations. So you realize that Newton's equation is a tensor of rank 0 equation, so rank 0. Einstein's equation is 2 ranks higher, right? Everything has 2 extra indices, it's rank 2. And I imagine that you spent all night lying awake in bed wondering, I wonder basically, is there anything in between 0 and 2? That would be 1. I'll do the math for you, okay? Any theory that we can think of that is rank 1? That would be electrodynamics, okay? And actually what we'll discover today is that electrodynamics, which sits conveniently between these two, is in some ways a perfect playground for us. Because what we'll do today is we'll talk about 3+1 decompositions, okay? And basically for 3+1 decomposition, for a scalar theory, there's nothing to do because a scalar is just a scalar. There's no tensor to decompose. Einstein's field equations, Einstein's equations, general relativity, that gets pretty messy pretty quickly, okay, because there's 2 indices to deal with. E&M is kind of perfect compromise between the two of them because there's something to do, but it's not as complicated as an Einstein equation. It's more transparent, and that's why we'll do a lot of that in the context of E&M. Okay. All right, so what we'll start with today is 3+1 decompositions. That will probably entertain us both today and tomorrow, and we'll go through all of that. Okay, so here is basic. I should start with my first page on that, though. Here's our second chapter. 3+1. Oops, and I was told to start right a little bit lower. So let me try that again. So why do we want to do that? You could argue that there's this really aesthetical beauty in Einstein's equations in unifying space and time into space-time. Why would we want to undo that? Why would we want to disentangle space and time again? Well, for many numerical approaches, we do that because we would like to cast the equations as basically what mathematicians would call a Cauchy problem. So we would like to basically have data at some instant of time, and then we would like to evolve those forward in time, okay? And basically one way of doing that is with a 3+1 decomposition, where we basically really separate all the spatial variables from the time variables. Now let's practice that first for a simple scalar field. So here's a scalar field. How would we do that for a scalar field? Well, let's start by writing down the scalar field equation, so that the block operator acting on some field psi, and just for the heck of it, I'll include some source term, the matter source term 4 pi rho on the right-hand side. Okay? Now, what do we mean by this block operator or the wave operator? What I mean by that is this. It's the block operator, psi. I define that as an A, nabla A. So these are now 4-dimensional covariant derivative operators, okay, acting on psi. So it's basically that's, okay, so the 4-dimensional divergence, if you want, of psi. What do we mean by this nabla operator with the index upstairs? Well, what we mean is that we raised one of those indices. So this is the same as GAB, nabla A, nabla B, acting on psi. Okay. And now we could do this. Actually, no, one more thing. Let's say we do this in special relativity, just to keep it a little bit easier. So in special relativity, we could simply replace the G AB with the eta AB. So in special relativity, this is the same as eta AB, nabla A, nabla B. And now we could do the space-time split. We would say, okay, I'll explicitly separate the time components in these sums from the space components. So the time component would just be eta tt, and then I have basically just the time derivatives. Oh, am I missing something? This is another test. You all failed. Okay, there's a psi, of course, missing, right? Sorry about that, okay? And now we have an eta tt, and in special relativity, these derivatives just become the second time derivative acting on psi. And then I have left over only the space components. So that would be n eta, ij. And now basically I'll replace the 4-dimensional covariant derivative operator with a 3-dimensional one. So these are now the spatial indices only, right? Okay. Spatial indices only, okay? And now I can remember that eta tt is -1. So this becomes minus partial t psi plus, now I define this operator as the d squared acting on psi, okay? So that's what this wave operator is. We've probably seen that before. It just gives us a wave operator, okay? That's what it is. Okay. Now I can insert this back into our field equation, okay? But instead of doing that directly, I'll first define a new auxiliary variable, which I call kappa, and that will be defined as the negative of the time derivative of psi, okay? And why negative? That will make more sense in a little bit, okay? And then basically I can write our equations as a set of first order and time equations, and actually I'll copy them all the way over here, okay? Because I want to keep them on the blackboard. And I'll use a fancy color coding, okay? So basically we'll have the one equation, which is just comes from the, oops, what is that, Chuck? Funny. One equation comes just is the definition of our variable kappa. So that gives me a partial t of maybe a red variable, which is psi. Oh, that didn't work well. Okay, I'm having some trouble with the red here. Psi, okay. That is equal to minus, and now on the right-hand side, I have the variable kappa. And then the other equation gives me a partial t of the green variable kappa, and that is equal to minus d squared acting on our red variable psi. Okay, plus, and now I can erase this, I guess. Plus, and then we have also a matter term, which I'll write in blue, maybe 4 pi. These are all the matter terms, 4 pi rho. Okay, so we have a red variable, a green variable, and then the matter terms in blue. All right. Now, we'll just leave that there for comparison with equations that we encounter later. I'll just say that basically why is it useful to write down these equations? Because what we should just take away for now is if we have the equations in this form, this is easy to solve numerically. Okay. Actually, we won't talk about numerical details in this lecture course, but I believe you will hear much more about that next week. Okay. But in a nutshell, what we could do is we could assume that we have kappas and psi at one time level. Then we could take numerical derivatives, like maybe use a finite differencing scheme or use a spectral scheme or whatever scheme you would like to use. You would evaluate numerically the second derivatives of these variables at your time level. Now you have all the right-hand sides for these equations. Then you can integrate them forward to the next time level. On the next time level, you do the same thing and you keep doing that iteratively. That's how you can construct your solution. Okay. So all we need to know for now is that this is a form of the equation that we can put on the computer and solve numerically. Okay. Now, having said that, though, is basically what did we really learn here? Not much, okay? Because in terms of a 3+1 decomposition, because of course we've been talking about a scalar. There's nothing to decompose into spatial and time parts for a scalar, right? So basically, yes, but we did split the equation itself, the field equation, into time derivatives and space derivatives, but that's all that we can do here. There's nothing more to do. In GR, we would also have to split all our tensors into time and space parts. So in order to get a taste of how that would work, actually we could now realize actually what we should, just to practice, what we should look at is our Maxwell's equations, because in Maxwell's equations, now we're dealing with vectors and we can practice decomposing those vectors, okay? So let's talk about Maxwell's equations or electromagnetism, okay? So here's part B, electromagnetism. So let's write down Maxwell's equations. Actually, does anybody remember them? How many are there? 4. Who offers me the first one? Okay, so the divergence of the, let's start with the E field, the divergence of the E field, and remember I'm writing the three-dimensional gradient operator as a D, equals 4 pi rho. This is also known as which law? Gauss's law, the guy with the mountaintops, remember? Okay, all right, so then this is the divergence of E, then there's also an equation for the curl of E, and that is equal to, does anybody remember? Excellent, that's right, minus, and then the time derivative of the B field. Does anybody remember the name? Faraday's law? Yeah, I think that's right. Then we have a nameless equation, which just states that the magnetic field has 0 divergence. Okay? And then we have another equation for the curl of B. Okay, and there we have basically, again, the time derivative on the right-hand side, okay, of E, but there's also a source term, namely the electric current density J. Okay? Now, one way to handle these equations is to introduce a vector potential. Okay, so what we'll do is we'll write the magnetic field as the curl of some vector potential A. Okay, and why is that nice? Because in that case, this equation is satisfied automatically because the divergence of a curl is identically 0. Okay, so let's write that down. Then we have the divergence of B is now the divergence of the curl, the curl of A, and that is 0. Okay. And now we also, so that deals with this B, we also need to deal with that B. That B will now be the following. We have the curl of B is now the same as the curl of A. Okay. And when you see something like that, what do? You look at the inside cover of your favorite E&M book, because there are lots of identities for all these things, right? Which we don't remember. But when you do that, then you realize you look it up, okay? And what you find when you look that up is that this is the same as the negative of the Laplace operator acting on A plus the gradient of the divergence of A. Okay, so that's the curl of B. Now I can basically, now we also have this equation. So basically the curl of E is the negative of B. Okay, so basically we then have the partial time derivative of D curl A. That's this, right? That's that term. That's equal to now, basically I can commute the time derivative and the spatial derivatives. So that gives, this is the same as D, or the curl of partial TA. And that, according to Faraday's law, is equal to the curl of E, or the negative of curl of E. Right? Now, looking at this equation, you think, aha, that means that the curl of A, the time derivative of A must be equal to E. But that's not quite true, or at least it's true, but not general enough, because we can add to that equation the gradient of an arbitrary function. Why is that? Because when we add a gradient to E, say, then taking the curl of that gradient will give us identically 0. Okay, so basically what this equation does is it implies that the time derivative of A is the same as minus E minus the the gradient of an arbitrary variable. And this is now our gauge freedom, okay? So basically we see that by rewriting the equations in this form, we pick up an arbitrary function that we can choose however we would like to, and that encodes our gauge freedom. So this is an arbitrary gauge variable. Okay. So what that means is we now have two evolution equations. There's one evolution equation here, and the other evolution equation is the one that we saw for partial E here. Let me write those down. Actually, maybe I'll do that over here. So our evolution equations. So these are equations that tell us about the time derivatives of our fields. Okay. So this is one. The other one we get, as I said, by solving for partial E here and inserting our expression for the curl of B. That tells me this is partial TE equals minus the Laplace operator acting on A plus D of the curl, the divergence of A. And then we still have the source term J, okay? These are two time evolution equations that tell us about the time derivatives of the field. But we still have one constraint equation left, namely Gauss's law, which tells us that the divergence of E must always be equal to that. Okay? And a constraint equation. Which is the divergence of E equals 4 pi rho. So here I wrote these equations in vector form, but last time we already practiced writing things in index form. So let me rewrite these equations in index form, but I'll do that over here because we'll keep it, and I'll use the same color coding. Okay, so basically we start, these were the equations for the scalar field. Now let's write them for the E and M. And you see the first equation is the time derivative of the variable A, which I'll again write in red. Okay, that's equal to the negative of another variable E in this case. Okay, but now what is new here is that we also have a new gauge variable, which I'll write in yellow. Okay. The other equation is the equation for E that is now our green variable, EI. Okay, equals, and now we'll have two terms. We have the Laplace operator, which is the same as that, which in index form I could write as DJ acting on AI, that's the red variable. But we have a second term, which is with the indices interchanged. There's a plus a DI, DJ, and an AJ down here. Okay, minus. And now we have the source terms 4 pi j. Okay. And then we also have the constraint, which is di, and then an ei equals, and then the matter source is 4 pi rho. Okay, I'm not sure why I'm writing the 4 pi in colors, but there you go. Okay, so so that's kind of neat. Okay, so basically you notice that basically the Maxwell's equations we can bring into a form that looks exactly like the one for the scalar field. We have the time derivative of the red variable, it's the negative of the green variable. Now you also appreciated why I defined the kappa as the negative of the time derivative of psi. And then we have the time derivative of the green variable is some second derivatives acting on psi plus source terms, exactly the same form. But of course, there are differences too. The obvious difference is that basically here we talked only about scalars. Here we now have vectors. So instead of carrying around only one field or two if you count the time derivative, now we have three for each one of those, the three components of E and A. Okay. The other thing that you notice is that, here we had only one term with second spatial derivatives. Now we have two. Okay. Basically all the kind of with the different indices in different positions. So basically different permutations of the indices, right? So that's a new thing. The other new thing is the gauge variable. The other new thing is the constraint, okay? The gauge variable is one free function. That's a rank 0 thing if you want to. Likewise, we only have one basically a constraint. And we see that actually that will go hand in hand together, okay? All right, so there we go. Okay, now we could be proud. Okay, now we did this 3+1 decomposition for the Maxwell's equations. But if you should think about it, you could say, come on, give me a break. We didn't do that really because we did something really rather silly. We started with the E fields and B fields, which are already spatial. So we didn't do any decomposition at all here, okay? So yes, we see that the equations take a beautiful form, okay? But really we haven't done anything either here. Okay. In order to do a 3+1 split of the fields, we would have to start with a genuinely four-dimensional object that describes these fields, and then we would decompose that object. Okay, right? So now we think, okay, can we rectify that situation? Can we think of writing the E and B fields in a genuinely four-dimensional object and then practice decomposing that? What would that object be? That is did I hear Faraday tensor? That's what I heard, right? So let's talk about the Faraday tensor. All right. Let me erase this. Okay, the Faraday tensor, C. And I keep writing too high, I believe, so let me start over, C. So what is the Faraday tensor? Well, it's FAB equals, and then basically we would have to look it up. Probably there's both basically EX, EY, EZ, and then there's minus EX, 0, BZ, minus BY. Then there's a minus EY, minus EZ, 0, BX. Okay. Minus EZ, BY, minus BX, and 0. I hope I got all the indices in science right. Yeah, we could have made this a little bit more exciting. We could have asked, how can we possibly basically accommodate the 6 components of the E field and the B field, 3 each, right, into a four-dimensional object? Clearly, it does not fit into a 1,4 vector because there's only 4 components. So we would have to go to a rank 2 tensor. A general rank 2 tensor in 4 dimensions has 4 times 4, i.e. 16 components, right? Yeah. Okay, this, what did I do wrong? So this is the Z, right? And oh, this should be a B, right? Is that what you're telling me? I agree with that. Yes. Is that better? Great. Good. Thank you. Okay. So basically, a general rank 2. Yes. Excellent question. Should there be another constraint? But because how about the B fields, right? Is that you're worried about? How do we respond to that question? What about the B fields? Should we count that constraint? You're right, of course. The diversity of the B field should be 0. Okay, why did I sweep that constraint under the rug? Because we express things in terms of A, right? And basically we wrote the B field as the curl of A, so the divergence of the B field is satisfied automatically, okay? So it doesn't count anymore, okay? We've eliminated by writing things in terms of A, but that's an excellent question. Actually, I have it in my notes to write, it's constraint satisfied automatically, but then I skipped it. I shouldn't have. Okay. Yeah, but very good. Yes.
In general relativity, there is another constraint like the covariant derivative of the energy momentum tensor going to zero. So is there a similar constraint in electromagnetism, like continuity equation?
You're about one page ahead in my notes. Okay, you're exactly. We're headed there. Okay, we'll see where that comes from. Okay, hold your question. Yes. All right. So okay. So basically, this is a lovely argument too, right? Basically, we have 6 components in E and B. We want to accommodate them in a 4-dimensional tensor. We could, just by counting degrees of freedom, basically what kind of a tensor could that possibly be? The general rank 2 4-dimensional tensor has 16 components. That's too many. Then we could think about, oh, maybe it's symmetric. Okay, if it's symmetric, it would be 4 plus 3 plus 2 plus 1. There would be 10 independent components. Still too many. So that doesn't work. Okay, it's saying, how about antisymmetric? And for an antisymmetric tensor, rank 2 tensor, in 4 dimensions, we have 3 plus 2 plus 1 equals 6 components. And like a smoking gun, right? It sounds like we're on the right track here. So that's basically the Faraday tensor. It's the object that accommodates our components. And actually basically leads us to a relativistic description of these fields, right? It is antisymmetric, as we just said. Okay, so FAB equals the negative of FBA. Okay. Also, by doing that, the diagonal components are automatically 0. We can then write Maxwell's equations in terms of the Faraday tensor. I won't derive this, but maybe you've seen that in the class, or maybe you can look it up in an E&M textbook, and you'll find that then we have basically the divergence of the Faraday tensor is 4 pi JA. I'll call this equation A. And then we have the completely anti-symmetric, the outer derivative, if you want, of BC, that is equal to 0, and that's equation B. Okay. And now I should also tell you what do I mean by this 4-dimensional J, right? This is now a 4-dimensional vector. Okay. Basically, we write that by that vector, we mean, actually, A, we mean the time component will be rho, and the space components will be our spatial charge density current. Okay. Now we come to your question. Okay. So basically, let's note something. There's something neat here. So basically, notice that if I take, this is the first derivative of FAB. What happens if I take a second derivative? Okay, so essentially if I take a divergence of this term, then I would have this. I would have nabla A, nabla B, FAB equals, does anybody see what this must be? It must be 0. Why must this be 0? So I think what I heard is that these 2 indices are antisymmetric. These 2 indices are symmetric. Therefore, the contraction of these 2 must be 0 identically. Okay. So this is a neat equation if you think about it. If you looked at the comparison, the counterpart of this equation in GR, you would call this the Bianchi identity. So let's call this the electromagnetic Bianchi identity. I call it E and B. Okay. So this is the, if you want, we call it the EM Bianchi identity. Okay. Now, I claim that this equation has 2 important consequences. One of them is exactly what you asked about. Okay. So this has 2 important consequences. One is the following. See, if I take what we saw here is if I take the divergence of the first divergence of FA, AB, I get identically 0. That means if I take a divergence of this equation, the left-hand side is 0, the right-hand side must be 0 too. That means the divergence of J must be 0 automatically. That is charge conservation. So we see that charge conservation is a consequence of that. Okay, so one consequence is charge conservation. Namely, nabla A, JA equals, and what is this? I could now split this into the time and the space components. The time component is partial T of JT, which is just rho, the charge density, plus the divergence of the spatial terms. Okay, that's 0. This is the continuity equation. It encodes charge conservation. So that's really neat. Okay, so charge conservation pops out of these equations automatically. There's another consequence. And the second consequence is the following. Let's say you had a vector and you discover that the vector has 0 divergence, say. Okay? Then you know that the components of the vector are not independent. Okay? Really, basically, if you have, let's say, all components except for one, then you can figure out what the last component is just from that constraint. Okay, so those components will not be independent. Likewise, basically, since divergence of this term is 0, that means that the components of these ones are also not independent. Okay, and that has an important consequence. But to see that more clearly, we'll do one more step. Okay, so basically, what we're headed here what we're heading towards is that. What we'll see is that the second consequence of that is basically the gauge freedom that we get here. And that comes hand in hand with a constraint. Okay, so there's a gauge freedom, and a constraint. Now, let me explain this. Okay, so let's first write FAB as again, in terms of a vector potential. Now it's a 4-dimensional vector potential. I write it as nabla A, AB minus nabla B, AA. Okay, now these are 4-dimensional nabla operators. Okay, why can I do that? Well, basically, this is the outer derivative. We write it as the outer derivative of A. This tells us that the outer derivative of this is, so basically it's just 2 forms, so that works automatically. So this equation basically tells us that we're allowed to do that, okay? And I'll skip over the details, but we could talk about that more if you would like to, all right? So basically, if this is true, then this equation B is satisfied automatically. We can disregard it, just like we were able to disregard the constraint for B, okay? And we only have to worry about equation A in the following. Okay, so then B is satisfied automatically. Okay, and A becomes the following. Okay, so basically what I'll refer to as the E&M field equation. This will be our field equation for our purposes. Nabla B, nabla A of AB minus nabla B of AA equals 4 pi JA. Okay, so let's put a box around this. This, if you want, plays the same role as the Poisson equation for Newtonian gravity or Einstein's equations for GR. In fact, if we want to push that analogy, we would notice that, okay, these are the second derivatives of our fundamental variable A. And in fact, they're the trace of the second derivatives. So they play the same role as the trace of like a tidal tensor. Okay, so we could find a tidal tensor here and do the exact analogy. Okay. Now, because of our Bianchi identity, we see that basically only. No, let me back up. Looking at this naively, you would count the number of equations that we have, and there are 4, right? For each value of A, for each choice of A, we have 1 equation. You say, great, so we have 4 equations. How many unknowns do we have? Well, there are 4, because there's 4 independent components in A. So you say, great, we can go home. We have 4 equations for 4 unknowns, we're done. Okay? But then you realize, but hey, wait, actually these equations are not independent because of this constraint. Okay? So one equation is redundant. It follows automatically from the other ones, right? Just like if you have the divergence of a vector field, okay? So that means that really, if we take that into account, there's only 3 equations here. So that means A is underdetermined. You have a question? Is it, so let me see. So this is nabla BA, B, BA. So these are interchanged, and there's an A. I think it's right. Okay, but let's check it later. Okay. All right. So basically, what that means is we have really only 3 equations, 3 independent equations for the 4 components of A. That means that one equation is redundant. Okay, and also we can choose one of these freely. Okay, there's no equation for it. Okay, so and that is a consequence of our Bianchi identity. So let me write this down. Okay, because of EMB, there's only 3 independent equations. Okay. That means that one equation is redundant, okay, meaning it is satisfied automatically if the other equations are satisfied, and that yields us, okay, what we mean by a redundant equation, that is a constraint equation. Just like this equation is redundant to the other ones, if we evolve these equations for valid initial data, this one will be satisfied automatically. It's redundant, okay? So that gives us, and we automatically get a constraint equation from that. Okay. But it also means that we can choose one component of AA freely. That is what we mean by gauge freedom. Okay, so what we see is that this Bianchi identity simultaneously tells us that there will be one constraint equation and one gauge freedom. They come hand in hand. Okay. This is a scalar equation. Therefore, it's rank 0. There's one constraint, one gauge freedom. In GR, the corresponding equation, the Bianchi equation, is a vector equation. Therefore, there will be 4 constraints and a 4-fold gauge freedom, which we refer to as the 4 coordinate, the 4 space-time coordinates that we have freedom to choose. All right? Okay. Now what we'll do is, why don't we fill in this column here? So basically, now we see that we have the same structure. We have as our fundamental variable here, we would choose A. The equations of motion are then given by this. They involve it involves the first derivatives. I'm sorry, for the equations of motion, that would be for the test particles. So a test particle would experience the electric fields. The electric fields are given in the Faraday tensor. They come as first derivatives of A. Okay, so just like, it's the same analogy. Then basically we could define a tidal tensor, which I could write as maybe EM, REM. This has now 3 indices because it has basically 3 components. It has B nabla A of AC minus nabla B nabla C of AA. Okay, and having defined this, we would then see that we can write the equation of motion B AB in exactly the same form as the other terms. Okay, it involves again a trace of the tidal tensor. It works exactly the same way. Okay, and that again suggests to us that we can play with this and explore lots of these properties. Right? Okay. Now I have a question for you. We're about halfway through. Okay. Would this be a good time to take a quick break, or do you just want to keep going? Let's have a vote. Who votes? Let's have a quick break. Who votes, let's just keep going, because it's so much fun. I think we have a clear majority for keeping going. All right, then let's do that. Because now we're finally ready to actually talk about 3+1 decomposition. So let's do that. Okay, so how would we now perform a 3+1 decomposition of these equations? Let's talk about that. Let me make some room here. Yes. Yeah, thank you.
This title tensor didn't come in the EMC.
Okay, say it again. I couldn't hear.
This title tensor,
Yeah.
Maxwell fields, it didn't come into pictures of us, right? Only its trace came into picture.
That's right. So basically what I did is I realized that I can write these two terms, okay, as a trace of a tensor that has a rank 3 tensor, which is these mixed second derivatives of A, right? So it will be this term. So basically just by creating an analogy to what we talked about yesterday, I basically called that this electromagnetic tidal tensor. Okay?
So, I'm asking because we introduced tidal tensor by motivating the change in distance between the two particles.
Oh, that's right. That's right. Okay. So basically, you ask. Okay. So your question is basically both here and here. Basically, we did that by looking at by the deviation of freely falling objects. You're absolutely right. We could do the same thing here. We could look at two charges. And compare basically if we let these two charges fall freely in an electric field, okay, or in electromagnetic fields, how would the distance change? And I believe you would get exactly this. You would encounter that object, okay? And it makes sense because the equation of motion for each individual charge is the Faraday tensor, which we write as basically this, as these antisymmetric derivatives of A, and then you expand those and you would get basically one more derivative which is encoded in there. Okay, did that answer your question? Okay, all right, okay. All right, now what did I want to do? I wanted to, let's erase this. Yeah, sure. Yeah, please.
Is there an analog in electrodynamics along the lines of the geodesic equations?
Yeah, I mean, basically, it would just be it's the Lorentz force, right? So basically, right. So basically, you write the F equals QE plus V cross B, right? So it's the Lorentz force would give you that. Right? Yeah. Mm-hmm. Okay. Yeah. Yeah. Let's explore it. Okay. So I mean, when you see, we've kind of seen it here that we have this phi, right? But actually, let's explore. We'll see that in the 3+1 decomposition. Okay. So we now want to perform a 3+1 decomposition. And now let me start by doing this. Let me say, okay, what I'll do is I'll just simply split the vectors, okay, into a time part and a spatial part. So for example, I could, and I think this goes in the direction of answering your question. Okay, I'll take this for vector A, I'll call the t component phi, and I'll call the spatial components AI. Okay, we've already done this for J. Okay, the source terms, we called the t component rho, that was the charge density, and we had the flux terms J. Okay, and so basically now notice what we're doing. We're doing the 3+1 decomposition 2 steps. In the first step, I split the variables. In the second step, I have to split the equations. Okay? So now we'll split the equations. Okay, and basically, let me start by doing first noting the following. Let's first note. Okay. Basically, how do I get the T component from FAB? Okay, and actually now I regret that I didn't do that. That I didn't leave FAB on the blackboard, but there's only that much room. But you have it in your notes. Remember, the FAB was in the first row of the Faraday tensor. Okay. So I can now get the T components by looking at the T components of the Faraday tensor. Okay, so basically you look up, in your notes you have FAB, you can check what I'm going to do. I'll say that EI, or EJ, I'll say, equals FTJ. Okay, so for example, if I want the X component, I would replace J with X, and then say EX equals FTX, right? So that means I go in the first column of the Faraday tensor and then the X component of that, and in your notes that should be EX. Now let me use capital T here for the time coordinate, and that will make sense in a minute too, all right? Now what is FTJ? Well, we wrote F as the outer derivative of A, so this is the same as nabla, big T, of AJ minus nabla J of AT, right? You agree? So now let's actually rework this a little bit. Let's basically again specialize to special relativity just for the moment. In that case, the spatial part of these covariant derivatives will just replace with spatial covariant derivatives, okay? And we'll actually make this more rigorous in a little while. How about the time derivative? That will just be the partial derivative with respect to time. But now what we have here is the time derivative with the index upstairs. So we have to worry about raising the index there, right? So that means that the nabla upper T becomes eta TA partial A, okay? But there's only one non-zero component here in the sum, which is when A also is big T. And eta TT is -1. So this is actually minus partial T. You agree? Okay. So if I insert all of this into my equation for E, then I get EJ equals minus partial T of AJ minus DJ phi. Huh, that is nice. Okay, that is, especially if I insert a minus here. Okay. And it's even better, okay? And you notice that's exactly the equation that we had here, just with the indices up, okay? So that's nice, we recovered that, we feel good about that, okay? So now, basically that was just the identification of E. That's the equivalent, we could have argued that that is essentially what we did here is we defined E as the time derivative of A. It's just an identification, just like here we defined kappa to be the time derivative of T. There was no physics in it yet, okay? So now, but basically see this is the first evolution equation we got from this, okay? Now let me look at the time component of EM, okay? So we haven't used this equation yet, right? So now let me look at the time component. So that means I will replace the A's with a T. Okay, so what do I get then? Then I get nabla. Okay, let's notice something. So we're replacing the A's with the big T. And then we have to add over all the B's, right? Notice one thing, if B takes the value T here, then I have in this term nabla T AT, but here I would also have nabla T AT. So those terms cancel. So when after having chosen A equals T, I can restrict the B's to the spatial components J only, all right? Because the T components cancel, right? So basically that means I now have nabla J, nabla T, AJ minus nabla J, A big T Okay, and what is that? Well, basically, that is the same. We can now use the same identification that we used a minute ago. This nabla t upstairs is a minus partial derivative. This is the spatial derivative. So this is the same as dj of both terms minus partial t aj minus dj phi. But that we just identified with E. That was E. So this is in fact the divergence of E. Okay. And that is equal to the time component of the right-hand side, but the time component of J is rho. So this is 4 pi rho. Okay. Which is the constraint. So that is nice. Okay. So we see that taking the time component of our field equation gave us the constraint equation. All right. Okay. Now there's only one equation left, and that is, let me see. Okay. Okay. So this gave us the constraint equation. Okay. Oh, I'm again writing too high. I apologize. Slow learner. Constraint equations. There we go. Okay. Now, what do we need to do next? Yes? Go ahead. We need to, so we just evaluate the time component of the field equation. Guess what? Now we need to evaluate the space components. All right, so now we evaluate the space components. Of EM. That means we set A to, let's say, I. Okay, now I replace the A's with I. Okay, and I will let you do that in the tutorial this afternoon. I think that would make a fine exercise. Okay, but you of course anticipate already what you should get if all goes well. You should get this equation. Okay, so you will verify that in the tutorial today. That you get the following: you will get partial big T, EI equals minus DJ AI plus DI dj aj minus 4 pi ji. Okay, so you will do this in the tutorial. And you notice that from this we get the second evolution equation. So basically to recap, we see that basically we get the first evolution equation, basically just the identification of E with the time derivative of A, by just looking at a component of the Faraday tensor itself. Okay, that's what we did here. Okay, we then evaluated the time component of the field equation that gave us a constraint. We evaluated the space components that give us the evolution equation. Okay, so we could be very satisfied and think, oh, we did really well here. Why don't we go home and have lunch or something like that? Until you think about it, wait, you know what? We're still not done here. I've led you through this whole sequence of, you could argue useless things, right? We started with the scalar wave equation. There was nothing to compose. Then I wrote down Maxwell's equation. You told me, but wait, the field's already spatial. There was nothing to decompose, okay? We said, okay, let's do let's start with the Faraday tensor. And we did that, and this is nice, okay? But you realize, actually, we have not done a general decomposition yet. Essentially, what we did here is the following. We basically pretended that we have the vectors in some coordinates, and then what I did is I split it exactly according to those coordinates. In a space-time diagram, that would look like this. Okay, so basically, let's say I have a space-time diagram like this, maybe X is here, okay? And basically all we've done for now is we've basically taken slices on which this coordinate big T is constant, okay? So basically we only decompose it according to our current coordinates already. There's no particular magic in that, okay? That was not all that exciting. The fun starts when we relax that assumption and say, what happens if instead we consider time slices that have a different shape? I don't know, maybe like this, okay? Or, you know, maybe a whole family of slices like that, where maybe now on these, we have a new coordinate, time coordinate, little t, which is constant. Why would you want to do that? In E&M, there's no particular reason for doing that, but in relativity, there is. And actually, you already had a taste of that in the tutorial yesterday. Because what did you do in the tutorial yesterday? You looked at Schwarzschild solutions, and you considered the transformation from the Schwarzschild time to some other time. What is that good for? It turns out these new time slices that you discovered there, which we refer to as trumpet slices, are extremely useful in numerical simulations. Okay, they allow you basically to evolve black holes like basically like magic. Okay, it works beautifully because of these special properties. So basically, but that means we need in numerical relativity, we need to consider time slices that are different from what we might have started with. Okay, and that's what we want to do now. Okay, so basically now we'll allow any spatial slices that have a different form, and we'll decompose our fields into these new arbitrary slices. Okay, so that's where actually really, if you want, the fun starts. Okay, okay, so we will now allow arbitrary spatial slices. And I'll call them sigma. Each one of these slices might be a sigma, okay? And we can define these slices as level surfaces of some function, okay? And that function will be actually our coordinate time t. I should add a footnote there, okay? That is not necessary, okay? But we'll do it just to make it a little bit more streamlined, and almost all, not all, but almost all numerical codes use the fact that basically the spatial slice will be aligned with the slice of constant coordinate time. Okay, so we'll make that assumption right away. We'll assume that our new slices are level surfaces of some function, and that function actually gives us our new coordinate time. Okay, so level surfaces of a function t, okay, which we will choose as coordinate time. And now you also notice why I used capital T a minute ago, because I wanted to be able to distinguish the capital T from our more general lowercase t that we use now. All right? Okay, the first thing that we will do with these slices is we will define the normal. Okay? Now, so basically here are our slices. This is a space-time diagram. So then the normal is a vector that is perpendicular on these slices. Okay? Now, I gave you a little exercise on the tutorial yesterday just to remind you that a normal in a space-time diagram is not the right angle that you expect from Euclidean space. It's kind of this funky thing. It's basically symmetric about the diagonal. Okay, so basically, if I drew a normal here, for example, it might look like this. Okay, so this is the space-time normal on this surface. Make sense? Okay. All right. So we define this normal vector. Okay. So let's call it n. Now, how can I find a vector that's perpendicular on a level surface? How can I always do that? How can I build a vector that is perpendicular on that? The gradient, right? So we write the normal vector as the gradient of our function t. Okay. But actually, what I'll do is I'll insert a factor, a normalization factor in between. Okay. And I also throw in a t. Why do I want to throw in a t? because basically the normal vector will be a time-like vector. And once I computed the version with the index upstairs, I want it to be future-oriented. So that the version with the index upstairs should have a future-pointed time component. And because when we erase this, it will be dominated by the gamma TT component, which is negative. That's why we're going to throw in a minus sign here, okay? So this minus sign just makes it future pointing, and this alpha is a normalization constant. Normalization constant. Okay. Now notice, because we're using T as our coordinate, if I now evaluate the coordinates of this vector in our new coordinate system, then the only component that is non-zero is when that index A takes the value T. And in that case, we get partial T, which is also known as 1. Okay, so that means basically this vector we could write as minus alpha 0, 0, 0. Okay, I said we insert this alpha to normalize it. Okay. That means that the dot product of n with itself, okay, which is the same as G, A, B, N, A, and B, that is, we want that to be -1. Okay. We good? Now, when we have a 4 vector whose magnitude is -1, that reminds us of a 4 velocity, right? Basically, that's exactly what a 4 velocity does. So we can think of this as the 4 velocity of an observer, and we call that a normal observer. It's an observer who would basically move through the space-time always in a direction that is perpendicular on the spatial slices. Okay, so we can think of this as a 4 velocity. It's the 4 velocity of somebody who we refer to as the normal observer. Okay. Now, let's think about something here. So let me draw a picture of 2 slices, maybe like this. Here's one slice. Here's another slice. And there's a normal vector, maybe that originates on this earlier slice, maybe labeled by T, whereas this one might be labeled by T plus dt. Now there's a normal vector that basically points in the future, something like this, and it basically intersects this new slice at some point. Okay. Let's say these 2 points are a proper distance d tau separated. And by proper time, I mean now the proper time that this normal observer would measure, right, on the wristwatch of that normal observer. So basically there's a vector that points from this point to here, okay? And this vector is now, it's aligned, of course, with the normal vector and has length d tau. So I call that d tau, okay? That's the proper length of this vector. The coordinates of this point are t and some spatial coordinates xi, okay? And basically what I'm now curious about is, okay, this vector will pierce this new time slice at a time coordinate time dt later, but that will correspond to a certain time d tau later for this normal observer. So we could now ask, how are these 2 related? How is dt and d tau related? Okay, and actually there's a simple way of figuring that out. So remember, if I basically, let's say I looked at the temperature distribution in this room, there's a temperature here, there's a temperature here. How do I figure out what is the difference? Okay, what I could do is I could evaluate the vector that points from here, from this point to that point, and I take the dot product of that vector with the gradient of the temperature distribution. So I compute the gradient of the temperature distribution here, okay, and take the dot product of that gradient with the coordinate displacement, and that gives us the change in the temperature. Now replace temperature with coordinate time. So if I want to figure out what is the difference between coordinate time here and coordinate time there, then what I do is I take the gradient of the coordinate time and take the dot product of that with the vector that separates the 2. Okay. So in this case, what is the vector that separates the 2? Well, that's NA times d tau. right, so basically what I'll do is I will do the following calculation. I observe that in a proper time d tau, okay, a normal observer measures the coordinate time to advance by dt equals, okay, and now again I need to take the dot product between the gradient of the function whose change I want to measure, that is the nabla at, right, times the vector that separates the two, that is na times d tau. Does that make sense? Do you see what I'm doing here? Okay. Now let's work out what that is. Nabla at, well, that's just that is na divided by minus 1 alpha, right? So this is the same as minus 1 over alpha, na. And then I have an na from here left over. And then I have a d tau, right? But now notice that na and a, well, that's just minus 1. That conveniently cancels this minus 1. So this is just d tau divided by alpha. Okay. So that now gives us, actually, maybe I'll leave that. That gives us an interpretation. What this alpha means, it tells us this normalization constant alpha tells us about the ratio in the advance between the advance of proper time and coordinate time between these two slices. Okay. We see that d tau equals alpha dt. Okay. And therefore, basically, because alpha now tells us how much proper time advances as the normal observer goes from one slice to the next, or elapses if you want to, we refer to this alpha as the lapse function. Okay, that's the lapse function. All right? What I could also do is I could figure out, okay, now we just worked out that when this normal observer goes from here to here, we worked out how much does the proper time change. We could also work out how much do the spatial coordinates change. So we can do the same calculation, but rather than evaluating a t here, we want to evaluate an xi, okay, the spatial coordinates. Okay, so let's do that. Okay, so before we do that though, let's do one more intermediate step. Let's notice the following. We said that the normal vector takes this form, okay? We're tied to that from our definition of the gradient and by having taken t to be our coordinate time, the level surfaces, okay? Now, what form can n then take with the indices upstairs? Well, the only thing that we know about n so far is that we wanted to satisfy this normalization. But that gives us a lot of freedom because what you see is that any vector that with the indices upstairs takes the form 1 of alpha times 1 minus beta I has the correct normalization. Right? Because when I take the dot product, all the beta terms will cancel out. You agree? All right? So what we'll now do is we'll use this form in figuring out what happens or how the xi's, the spatial coordinates change for the normal observer as the normal observer advances. Okay? So NA, also, that's next bullet. Okay, so NA also measures dxi equals, okay? And now basically we'll do the same trick, okay? I'll just replace the t with an xi. So this will be now nabla a of xi times na d tau, okay? The xi's are just labels. They label the spatial coordinates. They're just simple functions. So this is the same as partial xi, partial xa. That's what this thing means, okay? And then we multiply it with NA d tau, okay? But what is partial xi, partial xa? It is delta IA, right? It's the Kronecker delta. So this is the same as delta IA times NA d tau. That is the same as Ni d tau. And what is Ni? Well, Ni, we just saw, is allowed to be any, this beta. Okay, so this is the same as, did I miss an alpha somewhere? Oh no, I'm sorry. I'm replacing the d tau with alpha dt. That cancels d1 over alpha, and then I get minus beta I dt. Okay, there we go. So that means that what this beta measures is the rate at which this normal observer would would notice the spatial coordinates change. So basically what I'll do is I'll include another vector in here. Basically that goes from maybe here to there. Okay, so maybe we'll draw it in green. So there's a vector that points from here to here. This is beta I dt. Okay, so now this point would have the same spatial coordinates. Okay? So basically, if we went from here to here, we would leave the spatial components the same. The normal observer, on the other hand, sees the spatial components shifted in the opposite direction, pointing from there to there. So the spatial components here are t plus, no, you cannot read that. Let's erase that. T plus dt and xi minus beta I dt. Those will be the coordinates of that point. Okay. All right. So basically, we can think of one vector that goes along the normal. It will not necessarily connect points with the same spatial coordinates. But we could also introduce a new vector that connects points with the same spatial coordinates. Okay? We sometimes refer to that as the time vector, or we refer to that observer as a coordinate observer. Okay, let me see, where do I put that? Maybe over there. So the time vector would be TA, it's alpha NA plus beta A, and it has components 1, 0, 0, 0. Okay? So this vector would be tangent to a word line of a coordinate observer that connects points that all have the same spatial coordinates. All right. Now we're ready to actually split the space-time tensors into spatial parts and normal parts. Okay? So basically, let's draw a picture again, maybe of that. Okay, so basically, let's say we have, let me draw a space-time diagram again. Something like this. Here's our slice. Maybe this is a slice of constant t. Okay, I drew the normal vector. Or maybe I could do it in yellow too. Here's the normal vector. At this point, it may look like this. So this is NA, and sometimes I notice I do this squish kind of square to notify that it's perpendicular. Now let me draw an arbitrary vector on the same slice. Okay, maybe here's a vector A, okay? Oops, AA. And now we want to decompose this vector in terms of components that are parallel to n and that are aligned with the slice. Okay? So in this case, we would have one component that is parallel to n. That would be something like this. Okay? So this would be the component A parallel A. And now we see that that gives us this component, and inside the slice, that would be like this. Actually, maybe I should have used green. No, a different. Well, it doesn't matter. Orange, maybe. There we go. Okay. So this would be the component that is inside the slice, which I'll refer to as the perpendicular component, as in perpendicular on the normal vector. Okay. So let's talk about the decomposition of vectors. Maybe I can erase this picture now. Decomposition of tensors. So again, what we'll do is we'll write a vector or any tensor in terms of components that are parallel to n and they're perpendicular to n. So write, for example, AA equals AA parallel plus A perpendicular. Okay, all right? So let me define the magnitude of the vector that is parallel to n as phi. So basically phi would be, how do I do that? I would take the dot product between A and the normal vector n. Okay, that gives us the magnitude of the vector that is aligned, of the component that is aligned with the parallel vector. Okay, then A parallel, guess what? A parallel has to point in the same direction as n. So we already know it points in the same direction as n, and it has the magnitude phi, right? So the A parallel must be phi times NA, okay? Or if I insert the definition of phi, this is the same as minus NA NB AB. All right? By the way, why did I insert a minus here? Well, because n is a time-like vector. So for a future pointing A, this will give us a positive term, all right? Are we good with that? Yes? So why?
Phi in name.
Oh, why do I call it phi? Because you could call it lack of imagination, okay? But actually, what we'll see is that this will play the same role as the gauge variable phi that we found before, okay? So it's, if you want to, it's a little bit of anticipation, okay? So it will be the same thing, actually, okay? So that's why I call it phi, okay? But you could call it anything you would like to. Mm-hmm. Okay, so now the next thing we need to do, so we just computed a parallel, now we need to compute a perpendicular, but that we can simply do by computing the difference between those two. So a perpendicular is AA minus AA parallel from its very definition. But we just worked out what A parallel is, okay? So in a minute, I'll insert this expression for that, okay? But let's work on this first. Basically, let me use a simple trick. I can write GA, that's the same as G little g AB times AB, right? Why is that true? Because the metric with one index upstairs and one index downstairs is the same as the Kronecker delta. So this is the same thing, okay? It may not be clear what it's good for, but you probably agree that it's correct. Okay. And now from the A parallel, I insert plus NA and B, AB. Okay. And now you notice that both terms have an AB in here. In fact, I wanted an AB here. That's why I inserted the metric here. So now I can write this as G, AB plus NA, NB times AB. Okay? Sorry, where?
When you're substituting the wave path, whatever the phi is.
Okay, so I'm sorry, which phi E comes? Wait.
The phi NA.
Oh, the sign here? Oh, I'm sorry, I don't know what you're asking. Yeah? You're okay. So you believe that, right? It's good. Okay, good. All right. Okay. So now we have this. Okay, and basically, this now is an operator. You see what it does is basically I started with a space-time operator vector A. I act on this A with this operator, and it gives me just the spatial part. So what this operator does, it projects the space-time vector onto a spatial slice. And that's why we call it, guess what? The projection operator. Okay, so we just discovered that the projection operator is exactly this. That's why we needed to introduce the normal vector. Okay, so that we just discovered the projection operator. Okay. So I call it gamma. Gamma AB is defined as GAB plus NA NB. Okay. Again, it projects space-time objects into the slices perpendicular on A. Okay. Now let's see how. I think we still have a little bit of time, so let's do some example. Let's have some fun with the projection operator. Okay, let's work with let's see what we can do with this projection operator. So let's do a few examples. Okay. Well, one vector that we encounter is the flux density JA. Okay. How can I now project the energy current density? I'm sorry. Okay. JA. How can I project that, or how can I decompose this into its parts? Well, a neat way of doing it is by writing, again, inserting the Kronecker delta, also known as the metric with an index upstairs and one downstairs. So this is the same as GAB, JB. GAB times JB, right? Okay. Right. Then I insert the definition of the projection operator. Okay, I replace the G with gamma AB minus NA and B. So this is the same as gamma AB minus NA and B times JB. Okay. Now I split the two terms. The first term will be, actually, I start with the second term. The second term gives me an NA times minus NB JB. Okay. The second term, sorry, the first term gives me gamma AB JB. Okay. And now we define, basically you see the first part is again parallel to N. So this is what we call the normal component. Okay. This is what we might now define. Okay. You asked me before, why did I call it phi? Okay. Again, now a natural way of defining this would be rho, because it plays the role of the time component of our energy flux. So this would be rho. Whereas this we see is the spatial projection of J. Okay. And we might call this J perpendicular. Okay. A. Okay. It's the spatial part of our current density. Okay. Unlike before, this is now an arbitrary slice. However we slice it, this is how we could project those terms. Okay. What do this rho and J, what do they tell us? The physical interpretation of those would be the charge density as observed by a normal observer, and the current density observed by the normal observer. Okay. So these are the charge and current density as measured by NA. All right? How about we do one more example? Let's do something more interesting. How about we practice with a rank 2 tensor? How do we project a rank 2 tensor? Okay. So let's choose an example of a rank 2 tensor. And the example that I would like to look at is the gradient of NB. Okay. So basically NB is the normal vector, okay, on the slides. And now we'll look at the gradient of that. So it tells us, this object will tell us about how the normal vector changes as we're moving around in space-time. Okay? It may normal vector point in this direction here, but over here it would point in this direction. So as we're going in a different direction, basically the normal vector changes. Okay? This is a rank 2 tensor, a rank 2 space-time tensor. How do I now split this into space and normal components? Okay? Let's think about what we did here. Here, I inserted basically the Kronecker delta, okay, for the component A. Now we have 2 components. Should we all take a wild guess as what we'll do? Well, guess what? We'll use 2 copies of this Kronecker delta, 1 for each component. Okay, so I'll write this as G. Okay, now I copy the index A to one G, and then I sum over C's, and then I copy the B to the other G, and maybe I have a D, and then I have a nabla C and D. Make sense? Now, what do we do next? Well, we follow the exact same recipe. I'll replace G with gamma AB minus NA and B for each copies of this gamma, for this G, okay? So this is now gamma AC minus NA and C times gamma BD minus NB and D times nabla C and D. Do you agree? And you're checking for typos, I hope? All right, so now basically what we do is we'll work out what all these different terms are, okay? So what terms do we get? The first term that we get is basically if I factor out the gamma and the gamma acting on these 2. So this would give me a gamma AC, gamma BD, nabla C, and D. All right? The next term will be, okay, we get 4 terms, right, from the different products that we have here. I just wrote down this term. Now next, let me write down the product of these 2 terms. So that gives me a minus from this minus, gamma B D times NA NC times nabla C and D. Okay? Do you agree? Now the next term is, I'll take the other mixed derivative. That will be minus gamma A C N B N D times nabla C and D. And finally, I get a plus NA, NB, and C, and D, nabla, C, and D. All right? Okay, let's see. I think, I think I have a few more minutes. Is that right? Okay, so then because then we can finish this. So now I have 4 different terms. The first term, I will give a name. This term I will call, does anybody know what that is? It's the extrinsic curvature. Okay, so we refer to that as the extrinsic curvature. It tells us about the projections of the changes in the normal vector. But those, basically, the changes in normal vector tells us about how curved the surface is. If the surface is flat, then the normal vector doesn't change. So the curvature will be 0. On the other hand, if the surface is very curved, then the normal vector changes a lot. So that's why basically this term is a measure of the curvature of the surface. Okay? So we define the extrinsic curvature as KAB, and following convention, we'll insert a minus sign, gamma AC, gamma BD times nabla C and D. All right, so it's the spatial projection of the gradient of the normal vector. Okay? Now, what is this term? ND, nabla C, ND. Does anybody recognize what that might be? Imagine, just looking at this term, imagine we had a U here, 4 velocity instead of an N. Actually, you know what? I'm looking at the wrong term. I'm looking, let's look at this term, NC, nabla C, ND. So replace that with the N with a U, and I think I already heard it. It would be, it's the acceleration, right? So basically, this term is the same as the acceleration of a normal observer. So we define the acceleration of NA, which let's call it AA. That is the same as NB, nabla B, NA. Okay? Now, do you agree with the following? And note that NA, nabla B, NA. Actually, what is this? So basically, as a general rule, when I ask people, what is this? In 80% of the cases, the answer is 0, okay? So let me rephrase the question. Why is this? Does anybody see why that is 0? Because N is normalized, right? NA is 1. So if we take a gradient of that, we get 0. But we can also take the gradient as basically, we get 2 of these terms, identical terms. So this must be 0 because N is normalized, okay? And by the way, that also tells us that A must be spatial, because if I multiply this with NA, I would get exactly this combination. I would see it must be 0, okay? So hence, AA is spatial. And AA equals 0, okay? So what do we see then? Okay, then we see that the following is true. Okay, okay, so okay, this is okay, this is spatial. Okay, and what I should also add to that is that means if I take gamma AB, that must be the same as A, because A is spatial already. There's nothing else to project, so that's the same thing. Okay? So this first term, this term here, this gives me, this is AD, then I'm projecting that gives me AB. Then from the first term, I just have left over NAAB. Do you see that? What is the next term? This term is 0, one of the 80%. Okay. Why is that? Because we have an ND, nabla, ND. What is this term? Same thing, must be 0, ND, nabla, ND. So this is lovely. This cleans up very nicely, right? So these all the terms in the second line are 0. This is just KAB, and this is NAAB. So what that means is we have all of this collapses to nabla A and B equals minus KAB minus NAAB. Okay. All right. And basically, because I'm worried that otherwise I will forget, I'll just write one very quick note. From the definition of KAB, you can see that KAB is symmetric. So KAB is symmetric. That means that KAB is the same as KBA. Okay. Now, we covered a lot of mileage today. Thank you for staying awake. I appreciate it. I'm not sure I could have done that. But this is where we'll stop for today, and we'll continue this story tomorrow. Okay, there are several exercises where you go over some of the details, all of this, and you play with the projection operator. Okay? All right, all for today.
So let's quickly break for coffee for about half an hour and come back here at around 11:30.